the school year. So as you can see, last week we took our Unit 9 test, and then we went into evaluating limits, and we kind of went from there to, I would make sure you have all of those lectures, and again, these 3 lectures are all online. So if you missed or you weren't here, you could check the absent folder to get the handout for that day or the homework, and then you can re-watch those. Today, this week, we're going to be going over this second week. So note a few things. The first is I was going to have a quiz on Wednesday, but again, there was a language test, and then I believe this was the AP Stats this day. So what I'm going to do is these 2 days, I'm actually going to have like I'm going to give the quiz both days, because Lang is more of a senior thing, whereas the stats, I think more juniors are in it. So I think I'm going to do it that way, like give the same quiz both days, so people who can take it. Alright, and then on Friday we will have our review day, and then the Monday after that we will have the unit tests. And also note on that day, all the homework from May 6th, so this day until this day, May 13th, are going to be due. So I did that because, again, things are going to get kind of confusing. I didn't want to set like a date at the end of the week, and this is the one day everything's clear. And then we'll have our senior signing day, and then after that everything is just review. Alright, and then of course your corrections for the last test are due on the 20th of May. Alright, so as you can see up down here, check mark should mean that you've watched the class or seen it online at least once. So because you're here on May 9th, I'd go ahead and check off May 9th, because you're here watching the lecture. So, and I guess, yeah, so be sure to check that off. Okay, so let's talk about the lesson for today. So go ahead and turn the page. You have a do first. Again, I just wanted to run through these. So go ahead and do 1 through 4. I'll give you about, take about 4 minutes to do this. Yeah, so take about 4 minutes. Try to run through 1 through 4. Try to run through 1 through 4. What's up? Excuse me. Yeah, you should get back today. See, Carlo, Matt is not here. Okay. Anthony.
So that's the, so there's a science section on the ACT, but on the math section of the essay. No. More science questions than I would have. What would you do? Yeah, they go
What do you have to do at the top? So whenever you get that indeterminate form, you have to use factoring, right? Well, you're factoring an X out at the top, right? So that X squared comes from that.
So what did you just do one? Because the egg is cancelled out.
All right, let's look over these first three. I think I saw very few people get to the last one, but we'll talk about it. All right, so the first three here, of course, we learned on Friday that to evaluate a function, a function, all you really have to do is just plug in the value into the limit. And so here, 2 squared, you just plug 2 in there, 2 squared plus 1. 4 plus 1, that's going to be 5 here. For number 2, as we can see, so what you do is when you plug this in, when you plug 1 in, you get 1 squared plus 4 minus 5, which gives you 0, and 1 squared minus 1, which also gives you 0. So again, this form is called, what do we call this form? Indeterminate, right? Indeterminate form, because we don't know whether or not this limit exists at this point. So we have to go a step further. We have to use algebra to simplify the function to see if it indeed does not exist. So we see that the top is a quadratic equation, and the bottom is also a quadratic equation. And quadratic equations, you can use what to factor them? Xbox. You can use the Xbox here. So negative 5, 4, negative 1, and 5, which is right there. 1 and negative 1, which gives you x minus 1, x plus 1. X minus 1's cancel here. And so you're left with x plus 5 over x plus 1. And then that's going to equal 1 plus 5 over 1, which gives you 6 over 2, which is 3. All right. So again, anytime, I saw this on a lot of people, they gave up after the 0 over 0. No, if you get 0 over 0, you have to take a step further. Your test has failed, right? You have to simplify and take it further than that. All right, let's look at 3. So this is another factoring problem, but this is a little bit different of factoring, because rather than using Xbox in the top, because we don't have a quadratic equation, you're going to instead, all you have to do is just factor out an x. So you pull an x out of the top in the numerator, and that's going to give you x times x plus 1 all over x, right? So what cancels out here? Yeah, the x's cancel, right? There's an x up here. Those two will cancel, so you're just left with x plus 1. And then you get the limit as x approaches 0 of x plus 1. Then you just plug that in, and you get 1 as your limit for this problem. Okay. So again, that was just a review of the kind of skills we went over on Friday. So if you're still struggling with this, you need to do your homework and really focus on this lesson. Maybe even go back and watch the lecture. Okay. Let's go ahead. And since very few people actually got to 4, go ahead and try that out. Take about 1 minute. Try to just think about what's going on here. What would be the, like, what are we doing in this case? Okay, so let's talk about this. So here we have our graph. Here we have our graph which shows us a certain function. And we're basically asked to find the limit as x approaches 3 of f of x, right? Now note, that's a different question from finding f of 3, which is where I actually find whatever the value is at 3, right? So, what's the big word that we always see when we're talking about limit? It starts with an A. We do what to that point? We approach, right? Not apply, we approach that point, right? So whenever we see this, what is the limit as x approaches 3? What it's basically asking is, what is f of x approaching, that word pops up all the time with limits, as x gets closer to 3. The question is, what is f of x approaching as x gets closer to 3, right? Well, let's go ahead and look at this graph. So we look at the graph, we see from both sides here, so I'm approaching it, I'm getting closer and closer. What does it look like? What value of f of x am I getting as I get closer and closer to 3 from both sides? 2. I'm getting closer and closer to this 2 right here, aren't I? So the limit as x approaches 3 of f of x is 2. Now, however, we have to look at b. b instead is saying, what is f of x at 3? So it's not asking us what it's actually approaching. It's not asking us what the function is approaching at that point. It's instead asking us what it is exactly at that point, right? When I plug in 3, what do I get out? And so we look at 3. What is the value at that point? 3, right? The value is actually 3, right? And so I did this for 2 reasons. The first is to show you that when you're taking the limit of some function as it gets to a certain point, it could be the case that the actual value at that point is not equal to what it is actually approaching at that point. In this case, we can see that. It looks like it's approaching 2, but it's actually what at that point? 3, exactly. So everyone note that sometimes the value at the point is not the same as what it's approaching. Okay? So I just wanted to do that example. All right, let's just dive right in to the lesson for today. Sorry that took a while. All right. So let's continue this discussion of evaluating limits at infinity. Let's talk about what happens when you evaluate limits at infinity. So, let's talk about our old friend. So let's all remember our old friend. The limit as x approaches 0 of 1 over x, right? So all remember that guy, right? We've dealt with it a few times. Oh, not 0, sorry. Infinity. Let's talk about the limit as 1 over x as x approaches infinity. Right? We've all seen this function quite a few times. Now the big question that we asked ourselves when trying to solve this problem was, well, what happens to 1 over x when x gets really big? Right? What happens when x gets really big? Right? Because that's what a limit as x approaches infinity is asking, right? It's saying, what happens when x gets really, 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 really large, right, to this function? Well, we've kind of answered that question quite a number of times in this class, right? We've looked at its graph. Let's look at its graph real quick. Let's see what happens. We've looked at its graph. Kind of looks like this. Right? And we've seen that as x gets larger, so as x gets much, much larger, what's happening? Where is this function wanting to go? Not infinity, what? not negative. 0. Right? Because as the function goes that way, as it goes more and more this way, it looks like it's just going down, kind of trending towards the x-axis, right? Towards 0. So as x gets larger, f of x goes to 0. Right? F of x goes to 0. We see that graphically. We even can do what? Draw a table and see that, right? We can draw a table, our x, our f of x, put all these values in. 10, some easy ones. 1,000, 10,000. And it's like 0.1, 0.01, 0.001, 0.0001. And so we see as x goes to infinity, as it just gets larger and larger and larger, what's happening to f of x? What did we say? It does what? It does what? It approaches 0, yes. F of x is approaching 0. So we prove that multiple ways for the function 1 over x. Right? We prove that multiple ways. But what about problems that as we get older, right, things get a little more complicated, right? When you were younger, things were simple, right? You just wanted toys, some food, and like nap time, right? That was pretty much it. As you get older, you still need those things, but getting those things becomes what? A little more complicated, right? Same for math. Now that we've gotten older, we have to look at functions, say, like this. The limit as x approaches infinity of 6x minus x over 3x cubed plus 1. Right? This is a little more confusing. Because one, I can't just enter in some simple values into this. I can't just keep entering 10, 100, 1,000 to try to get the same thing. Right? And graphically, I would need a graphing calculator, and judging by the way some of you use your graphing calculator, that might not be the best choice because you might put a negative sign in someplace, right? So, the question for today is there a way to algebraically, if I can spell this correctly, kind of, find limits at infinity? The question for today is there a way algebraically? Is there a way that we don't need the table and the graph to figure out where these limits as they go to infinity go? Right? That's the question. That's the million-dollar question for today. And of course, it's kind of obvious. If a teacher's posing a question like that to you in a class like this, what do you think the answer is? No. Yeah, no. All right, guys. See you later. Have a good time. No. What's the answer? Yep. Yes, the answer is yes. There is an algebraic way. And that's going to be what we're going to talk about today. So let's talk about the key concept for today. This is the thing we need to take away to do our homework and to be successful on the unit test. So, key concept is this. If we have a limit as x approaches infinity of axm plus some stuff. I really don't care about that stuff. Over bx to the n power plus some stuff. And that thing is my function, right? So if I'm taking my function to infinity, so if I take the limit of x as it goes to infinity of this function, that has a mx in the top and bxn in the bottom, there's going to be three cases. There's going to be three cases that I need to worry about. First one is if the exponents in both the numerator and the denominator, if the highest exponents in the numerator and the denominator are the same, then that implies that the limit as x goes to infinity of this function is just going to be the coefficients of the exponents. So this is going to be a over b in this case. So again, if the highest exponents in the numerator and the denominator are the same, then that implies that the limit as x goes to infinity of this function is going to be the two coefficients over each other. Yes, Miranda?
I have a question. At the top where it says equals f of x, that's just for the equation.
What's that? Where it says f of x?
Yeah, that's...
Yeah, it's just saying this is our function right here.
Okay.
We're defining that as our function. Okay, next case. If m is greater than n, so if the exponent in the numerator is bigger or higher than the one in the bottom, then that's going to imply that the limit as x goes to infinity of this function is going to be infinity. Now we got to be careful here, because how many kinds of infinity are there? There are two kinds of infinity. One is positive, the other is negative. So, it could either be positive or negative infinity, and when we do our model problem involving this equation, or involving this kind of problem, I'll tell you how do you distinguish whether or not you're going to positive infinity or negative infinity. Alright. Number 3, m is less than n. In that case, so in this case, what would this be? The exponent where is higher? The exponent in the bottom is higher, right? Because m is less than n, or n is greater than m, right? In this case, then the limit as x approaches infinity of this function is going to be 0. Is going to be 0. So those are the 3 rules we need to remember. If we're taking a limit as it goes to infinity, those are the 3 rules we need to remember. Before I go on, any questions over this? Again, we could talk about the intuitiveness. We've talked about the intuitiveness this before. 3 is pretty easy, because if you think about it, if something in the bottom has a higher exponent than the top, then as the numbers get larger and larger, the bottom is the only thing that matters. Small number over big number goes to 0. So, let's turn the page. Let's look at some model problems. Let's look at some model problems. Let's look at the problem, the limit as x approaches infinity of 4x plus 5 over 8x minus 3. So this is going to be our first problem. And again, you're going to like these, because these are actually these are very simple, right? Because, so, all we got to do, exponent, numerator, denominator, which one's bigger? They're both the same, right? So, in that case, what do we have to do? Yeah, we just look at their coefficients, right? Whatever number is in front of those x values. So we just look at this, and we say, okay, well that's 4 over 8. And what is 4 over 8? 1/2. Belongs to the 1/2 club. Exactly. So this limit x over x is the limit as x approaches infinity of this function. If you go all the way out to really big numbers, it will start approaching 1/2. Okay. Let's look at example B. Let's take the limit as x approaches infinity of 6x squared minus x over 3x cubed plus 1. So now we're looking at this limit here. So what's the dealio here? What degree is bigger, bottom or top?
Bottom.
The bottom is bigger, right? So when the bottom is bigger, what does that mean? It's 0. It's 0. Alright? When the bottom is bigger, that means that the function, the limit as x goes to infinity is 0. Right? And again, it makes some sense, because if the bottom is bigger, then those numbers are going to get large much, much faster than the top, and if you have a very small top of a fraction over a very big, that's going to be pretty close to what? 0. Exactly. One more, and then I'll let y'all loosen some problems. Let's talk about the limit as x approaches infinity of 5x to the 4th over 9x cubed plus 2x. Right? So this is 5x to the 4th over 9x cubed plus 2x. Now, what's the case here? Which exponent is larger? The top is. So because the top is larger, this is going to go where? This is going to go to infinity. But again, we have to be careful. Because there's two kinds of infinity. There's negative and positive infinity. So how do we know which one it goes to? Well, the key is you're going to look at the highest exponent one. Particularly in this case, it's always going to be in the top because obviously you're going infinity. So let's look at x to the 4th. Now, if you recall from a long time ago, when we did functional analysis, we talked about how every function that has an even power is always going to have the same in behavior, right? X to the 4th is going to look like x squared and x6, right? So, what does x squared look like? What does a parabola do? It does what? It's like a U or bowl shape to it, right? It's like a U or bowl shape. So, x to the 4th looks very similar to that. So if I were to draw x to the 4th power, it looks very, very similar, except it has a few curves in the middle here. But we don't care about what's going on there. We only care about, as this goes to infinity, is this going up or down? It's going up all the way to positive infinity, right? And so because this graph is going to positive infinity, that means that this limit must be going where? Also to positive infinity. And so that is the 3 examples. So that's what you would do. All right. Any questions over any of these model problems? Okay. Take about, it doesn't take you long at all, as you just saw. Take about 2 minutes. Go ahead and run through A, B, and C. Go ahead and give a shot at A, B, and C. All right, let's talk about these answers. So if quite a few people got it, that's good. If not, that's okay. Let's look at the answers. So, number 1. Now, the reason I threw this one in here is because some people get confused by the fact that there is no x in the top. But when there's no x in the top, obviously, and there's an x in the bottom, having an x itself means that you're of a higher degree of x than the top, right? So you could just assume that the x is bigger than the bottom, and so 0. One other way I like to explain it to people is that maybe you can think of having an x to the 0 power in the top. What is x to the 0 power? It's 1. So you can maybe think of it like that. 1 is bigger than 0. That might be another way to think about it. For b, which one is higher? The top. And so obviously it's going to go to infinity. However, we look at our graph. Now, when you put a negative, normally a parabola looks like a bowl. But when you put a negative in front of it, what happens? It flips over, right? It looks like a little hill, right? And so because of that, as that shoots off to positive infinity, it's going to shoot down to negative infinity instead. So in this case, we're going to be going to negative infinity as opposed to positive infinity. Last but not least, C. Last but not least, C. Which one's bigger, top or bottom? They're the same. They're the same. So when they're the same, you take their coefficient, 7/2. This, as x gets larger and larger, will converge to 7/2 or 3.5. Okay. Any questions on this? Any questions? It's fairly straightforward, right? Okay. Let's look at one application problem, just because I thought this was very interesting and might help to kind of think about why are limits useful, or why might they be useful in science, right? So can I get a volunteer to read, go ahead, read through A.
According to the special theory of relativity developed by Albert Einstein, the mass of an object traveling at the speed of v is given by the equation m equals dash. First is the speed of light, and is the initial or reference of the object. Find the limit, then use it to explain the relationship between the limit and m.
Yes, good. So, first off, let's just observe how weird this equation is, right? Let's just observe how weird this equation is, right? Because first of all, what is this equation giving us? What is m? It's the mass of the object, right? So you can think about it as yourself, right? You weigh a certain amount. Or this pen has a certain mass to it, right? It's grams or grams, right? Yeah, newtons is force. Grams. Notice there's an initial or some sort of normal mass that you have, but your mass is also affected by two other things, right? What else is your mass affected by? What is V? Your velocity or your speed. So think about that. The amount that you weigh, how much that you impress, the amount that you take up in space, depends on how fast you're moving. Kind of weird, isn't it? What else is it dependent on? What's C? The speed of light. So the mass that you have, that your body holds and that this pen has, is dependent on C, which is the speed of light. Again, that's kind of a weird thing to think about, right? How does your mass, which we normally think of on Earth being constant, right? Your mass doesn't change based on how fast you're moving on a train or a bus, right? You're the same weight. But for some reason, this equation is saying, no, your speed is affecting your weight, right? So, if I'm finding the limit as v approaches 0, so I'm going to say the limit as v approaches 0 of all this stuff, right? First, let's talk, what does it mean to say that the limit as v approaches 0? What does that say? What is that saying? What's that?
How can velocity be negative?
Well, it's not negative, it's going to 0, right? It's approaching 0. So if the velocity is approaching 0, what does that mean? You're slowing down, right? You're slowing down to a stop, right? You're slowing down to where you're not moving at all. Okay? So, alright, well let's see what happens when you slow down. Let's see what value you would approach. Okay? So, as I slow down, v goes to 0, so what am I going to do with that? What's that? Good. For velocity, I plug in what? 0. So let's do that. So, your initial mass over the square root of 1 minus, again, your velocity is 0. You're going to get over the square root of 1. And so as you approach 0, as your velocity approaches 0, as you slow down more and more, you approach what? Your initial mass, or the rest mass. And that makes sense, right? Because if you're going to 0, if you're going to stop, if you're going to rest, then it should make sense that your mass would approach your rest mass, right? That makes complete sense. Here's where things get really interesting, is part B. Anthony, can you read part B?
What happens to the mass of an object if we were able to approach the speed of light?
Okay. So, there's that word, approach, again. So, what does approach mean? What is it always associated with? Not smaller. Starts with an L. We've been doing it. Limit. Approach means you need to find the limit. So, the limit, what's approaching? Speed, which is v, is going to approach what? Is going to approach what? The speed of light, which is c. So v is going to approach c. So we're going to find the limit as v approaches c. Okay? So we plug this function in. Right. All right. Go ahead.
Wouldn't it be like 1 minus c squared over c squared?
Yes. Okay, good. So how'd you get that? Because you plugged in what?
C into the v?
Yeah. So we plug in c to v because we're evaluating this limit. So let's do that. Minus c squared over c squared. Okay. Of course, anything over the same over itself is what? 1. So we get. What's happening here? You're getting 0 down there, right? Now again, remember, that isn't too bad because we're taking the limit. We took the limit as this approaches 0. So, if you get 0 in the denominator, so you have a number in the top and 0 in the bottom, what is that function going? So think about it. Really big number in top, small number in bottom. Where is that going off to? It's shooting off to infinity, right? The top is just growing, right? It just stays the same as the bottom gets infinitely small. So this is going to shoot off to infinity. Now what does that mean? What's that? The mass gets infinite as what? As what? So we're on a spaceship, right? We're on a spaceship going towards the speed of light, and we're approaching the speed of light, right? That's our velocity, is approaching the speed of light. So, if we're approaching the speed of light, what is this saying is going to happen to the ship? What's going to happen to the weight of the ship? It's not going to get lighter. It's going to get heavier. In fact, it's going to get how heavy? It's going to get infinitely heavy. So your ship, your body, everything on that ship is just going to become so incredibly dense. And why is that? Well, the reason is because the speed of light, the light that you see around us, we cannot go past that. No matter, nothing can go past that speed limit. That is the speed limit of the universe. If you try to approach it, what's going to happen is exactly this. You're not going to go any faster. You're going to get weighed down more and more and more. And as you approach it, you will actually get off to an infinite weight, right? Now, yes, you will actually get crushed completely because your body could not handle that amount of density. Now, even further, here's the crazier part. If it is the case that your matter becomes infinitely dense, right, and light is the speed limit. Oh, recording. What am I doing? If it is the case that you're getting infinitely closer, and your mass gets heavier and heavier. So, does that mean that your body and all the things that you're having around you, all the things you're touching, the matter, is there some relation between all of that stuff, the stuff that you see, touch, the people that you love, the things that you do, the things that you enjoy, all of that stuff, is that in some way connected to the light that's coming in this room? You see all of this energy? Is that in some way connected? Is light in some ways connected to the matter? Yes, in fact it is, through this equation. And this actually is what answers our questions about the Big Bang. The Big Bang was just a huge explosion, and as weird special things that Mr. Terry could explain to you happen, it turns into matter, which eventually forms all the planets, stars, and everything that you see. Alright, so that's it. Did you have a question, Chris? Sorry. So, anyway. So, next page, you got your homework. You can see there's quite a few problems there. But as you saw in the modeling, this got pretty easy. You were able to do it pretty quickly. So again, this is due May 16th along with all the other homeworks. Yeah, so due May 16th. Answer keys on the back. Alright, and again, if you need to take your test, please come see me or talk to me. The unit test we took last Wednesday.